basically, we've been looking at 5.5 and 5.6. I'm going to continue with some more examples from those sections. And then we're going to do a little bit of 5.7 later. So just a bit of a warm-up. So suppose we flip 10 coins. How many different outcomes are there? Okay, and I'm going to think of this as flipping the coins in order. So like I flip a coin, and I flip another coin, and I care about not just how many heads there are, but what order the different outcomes are. Okay, so okay, so there's 2 outcomes for each toss, or for each flip. So for the first flip, there's 2 outcomes, etc. You have 10 flips, so you've got 2 to the 10 outcomes. But now suppose I modify this a little bit. I say, how many outcomes have exactly 3 heads? Any thoughts? So this is somehow going to, like a lot of the problems we've been doing, this is somehow going to involve like permutations or combinations or something like that. So any idea how to think about this one? Yeah. Well, it could be the first 3 are heads, but it could be the last 3 are heads, or it could be lots of different, there's lots of different possibilities there. Well, oh yeah? Okay. Well, if we kind of, so I'm thinking of all these coins as being different somehow, right? So anyway, so we've got like 10 positions. Each of them can be heads or tails. And to have exactly 3 heads, it's the same as picking, 3 positions to be the heads and then putting the tails on the rest of them. Right, so it could be the first 3 are heads, but it could be the first 2 and this one is a head. It could be anything, right? So, but there's 10 choose 3 ways to choose which 3 coins are heads. Okay, so that's going to be your answer, which simplifies to 120. So if you put 10C3 in your calculator, you'll get 120, hopefully. So, okay, so these are 3 different ways of writing the same thing. It's 10 choose 3, 10C3, but the raw number is 120. Okay, so given this, so if this is how you count outcomes with exactly 3 heads, what about it if you wanted at most 3? And by the way, I recognize that all these counting questions are really tricky. It's going to take you a while, a lot of practice to get your head around these things, but I'll keep kind of reminding you of these things. Yeah. That's kind of 99% of it. You got to not forget 10 choose 0 as well. You could have 0 heads, right? So if there's at most 3 heads, there's either, just to repeat that, there's either 3 heads, 2 heads, 1 head, or 0 heads. And then you just add up all those possibilities, because they're all kind of disjoint possibilities. So 10 choose 3 would be 3 heads. 10 choose 2 ways to have exactly, so this is like exactly 3. This would be exactly 2. Plus 10 choose 1 plus 10 choose 0, which is 120 plus, I think, 45 plus 10 plus 1. Maybe it's 176 or something. Right, because if you got at most 3 heads, you got exactly 3, exactly 2, exactly 1, or exactly 0, right? Now here's one that seems like it could be pretty annoying. What if I say at least 3 heads? Yeah. Okay, I don't know for sure if there's a simpler way or not, but that seems simple enough for me. Yeah. Right, so yeah, that's kind of the trick. So you could see multiple ways of doing this, right? You could add 10 choose 3 plus 10 choose 4, 10 choose 5, ... up to 10 choose 10. So kind of method 1, I guess. But I wouldn't really suggest this one because it's going to take you longer. But you could just take but then you've got to add up like 8 numbers or something like that. But I like the proposal that was just given to us. If you want to have at least 3 heads, that's the same as not having 2 heads or 1 head or 0 heads. So if we take all the outcomes, which is 2 to the 10, right? We already computed at the beginning there are 2 to the 10 outcomes in total. So this is this kind of count the complement thing, right? If it seems complicated to count something, then you might want to think about counting the things that don't satisfy the criteria and subtracting. So if I take everything minus the ones I don't want to count, so I don't want to count the things with 2 heads or 1 head or 0 heads, you can see that this is a little bit simpler than that, right? And then okay, this is, I think, 1024. Which, whatever that works out to be, 900 and something. Any questions about what just happened? I kind of went through that a bit fast, but. Right, so this is all outcomes. Minus the outcomes with 2 heads, exactly 2 heads, exactly 1 head, or exactly 0 heads. By the way, this is something like, yeah, don't forget about the 0 case, right? There really could be 0 heads. Any questions about that? Okay. Let's now do another counting type problem. So this one's going to be involving like walking through a grid, basically. Okay, so here's the kind of game we're going to play here. So we start at the point 0, 0. And we're going to walk to the point 4, 6. And what you're allowed to do at each step is you can take a step upwards, or you can take a step to the right by 1 unit. Okay, so you can't go diagonally. You can't do any crazy thing. You can't walk left. You can't walk down. So in each step, you either go up by 1 or to the right by 1. And what I want to work out is how many different paths are there starting here and ending here that only take steps 1 to the right or 1 up. So how many ways? So how many paths are there from the origin 0, 0 to 4, 6 that only take steps of length 1 in the positive x or the positive y direction? So one path, you could just take 4 steps up, or sorry, 6 steps up in the y direction, 4 steps in the x direction. Or you could take a step to the right, a step up, a step to the right, a step up, up, right, up, or something. Okay. So just like a lot of these problems, the trick really is finding the right way of analyzing it and kind of breaking it down. Can anyone see what the answer might be? Is the question clear? That's exactly the right place to start. Yeah. So yeah, in case you didn't catch that, no matter what you do, you're going to be taking exactly 10 steps from there to yeah. So there will be 10 steps total. For every possible path, right? There are 2 ways to take a step, up or right. But here's the thing, suppose I take 10 steps up in a row, that's going to be a bad possibility. You're not going to end up at the right place. Any? Yeah. Oh, yeah. Order matters, but yeah, 24 is not really going to come into this at all. What was your idea? Well, so if you did 5 to the right and 5 up, you're not going to end up here. You're going to end up over here or something at 5, 5. So you will always take 4 to the right at some, if you end up taking 5 to the right, you end up over here and you can't get back, right? So that's the next kind of thing to notice. 4 of the steps. That's exactly what we kind of want to recognize here. Four of your steps have to be to the right, 6 of them have to be up. There's no other, if you take only 3 to the right, well, you're going to have to take 7 up, and then you're not going to end up there. So does anyone see the answer? Yeah? Yeah, no, it's not just going to, 24, I mean, in some sense, in a grid, 24 does come up naturally as somehow the area of this grid, but that's not going to count the number of steps, yeah, or the number of paths. Yeah. So very close. So actually, you don't need to multiply at all. It's just going to be 10 choose 4. So the way to analyze that is you've got, so once you choose the step to the right, then everything else is a step up. So there's no additional choices. So yeah, you can think of it as, every path, you can think of it as a list of instructions. That could be like, up, up, right, right, up, up, right, up, right, up, for example. And here I've got 4 rights, 6 ups. So this is the same thing as choosing a sequence of rights and ups that have exactly 4 rights is the same thing as choosing a path. So the U stands for up, the R stands for right. Yeah? Yeah, that's a good point. We haven't really addressed that, but actually 10 choose 4 is the same thing as 10 choose 6. So if you came up with 10 choose 6 as your answer, that's not wrong. It's the same as 10 choose 4, because taking 10 things and choosing 4 of them is the same as not choosing 6 of them, which is the same as choosing 6 of them, kind of. Oh, so the choose formula, right, is 10 factorial over 4 factorial, 6 factorial. Yeah, which you can also switch those around, and then you can see that these are the same thing. If this will be 10 factorial over 6 factorial, 4 factorial. But those are obviously the same, because multiplication is commutative. You can just switch them. So that's like an algebraic reason why they're the same thing, because they've got the same formula. Right, so this is the way to analyze this. You can think of it, you've got 10, you're going to do 10 steps. Exactly 4 of them are going to be to the right. So all you get to choose is where, like at what points are you going right. So it's just choosing 4 things from this list of instructions to be right steps. Okay, so yeah, so the answer is, if you put it in your calculator, it's 10C4. Any questions about that? Okay. All of these things just come down to, once you can see it the right way, it's not that hard, but the hard part is seeing it the right way. Okay, still working. Okay. Okay, let's do a twist on this problem. So how many paths? So still paths from 0, 0 to 4, 6. Have no consecutive like steps to the right. So if you take a right step, you're not allowed to take one immediately. You have to go up first, and then you can go right again. So yeah, we're looking at things like up, right, up, right, up, right. You know, for example. There might be a way to do it like that. That's not the way I would suggest for this one, though. Yeah. Yep, yep. So that, by the way, just to address another idea that was, so you're also saying to use right up as a letter. I would be careful with that because you won't end up with being able to put a right at the end. You know, you could have a right as the last letter as well. So I like this answer. What you can do is you can just take your ups, list out all your ups, there's 6 of them. And now what you're allowed to do is you're allowed to insert rights into this, but you can't insert 2 rights in the same slot. So if I think of my kind of slots, I've got one before the first U, between, you know, consecutive U's, or at the end. All I'm going to do is pick 4 of those slots and stick in rights. And that's the same thing as where I don't choose the same one twice, right? You have to choose 4 of these without repetition and stick in rights. And that's the same thing as having a sequence with no consecutive rights. So 7, choose 4. Ways to choose the positions of the R's. Yeah. Okay. I think the only way to get good at these things is get a lot of practice. Get feedback. Like if you go on the MyLab Math system, you can, you know, attempt these problems. You might have, the first time you do it, you might have the wrong way of thinking of it. You enter the wrong number, it's going to tell you it's wrong. Try to think of it a different way, and maybe, you know, one of these ways eventually should work. Yeah. Any questions? Yeah. Okay. All right. Okay. What if I said, just another slight twist, so what if I said, how many ways do you have at least like 2 consecutive rights? So how many do have consecutive right steps? Yeah. So they could all be in a block, right, 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 right. They could be right, right, and then no other consecutive rights, or any kind of combination. Yeah. Oh, sorry, I didn't completely hear that. Yeah. Yeah. So here you could get into a whole rabbit hole if you just try to count this without thinking about the previous 2 solutions. But if you're, you know, the quickest way to do it is just say, oh, well, that's kind of the opposite of this thing. And I've already computed the whole total, which was 10 choose 4. So now I just subtract. That's the quick trick here. So 10 choose 4 minus 7 choose 4, because this is all possibilities. And this is with no consecutive r's. Okay. And trust me, if you did try to do this kind of from first principles, if you were just maybe trying to glue two r's together and then count possibilities, there's a lot of places to make mistakes with that. I wouldn't recommend doing that for this question. Because you have to think of, oh, what if 3 r's are together, and what if 4 r's are together, and all these different. I wouldn't recommend it. It is possible eventually to get the answer. But again, if you have a problem where you think this is going to be really complicated, the trick might be just to say, what if I just count the complement? I just take the total and subtract the ones I don't want to count. Right. All right. Okay. So yeah, you can put this in your calculator and compute it. And that'll give you some raw number. You can compute this one. I don't think I wrote these ones down, but whatever that gives you, and then just subtract whatever that gives you, basically. Well, okay, so I think probably if you just wrote this on a test or something, we'd probably be okay. But like MyLab Math wants a number, so if it was a quiz, you need to write it like this, or you need to compute the final number. Any other questions? Oh, sorry. I wouldn't try to type this into MyLab. No, I would just compute the actual number. Yeah. Especially because the textbook doesn't use this notation. This notation's from your calculator, but yeah. I also probably wouldn't input this because I don't think MyLab Math is going to compute things like this for you. So, yeah.
It does let you enter formulaic stuff.
Yeah. Yeah, and I think it's probably quite restricted in what it will accept. Like maybe it'll only accept the formula in one specific way or something. Yeah. So I can't really predict what it's going to do if you put something like that in. Okay, so another example. You got 15 balls in a bin. Which are numbered 1 to 15. Okay, so they've got numbers on them. And then let's say that 10 are white. 5 are red. So we pick 5 balls from the bin. How many outcomes have exactly 3 red balls. Okay. Okay, so here, it's kind of important that the balls are numbered. So when I pick these 5 balls, not only can I see the colors of them, but I can also see which balls they were, right? If they didn't have numbers, if they were all identical balls, this would change the question. But yeah. Okay, any ideas? Yeah? Well, some of those numbers are going to show up, but yeah. Yeah, that's not quite what you want, but any other thoughts? Yeah. Ah. You might be able to analyze that. Not quite. So maybe I'll show you how to analyze this one. So yeah, but the idea that was mentioned was you could take 15, choose 5, and then try to subtract the ones that you don't want to count, and that kind of thing. In this case, it's not too bad actually. If you think about your 5 red balls. There's going to be 5 choose 3 ways to pick 3 of them. So that's the number of ways to pick 3 red balls. You can think of it, kind of like a 2-step process. We're going to pick 3 red balls and 2 white balls. From the white balls, there's 10 of them, and you're choosing 2. So in this case, actually, it's easier to just analyze this one directly rather than counting the complement. Yeah, that's a good question. So the balls weren't numbered. We change the total number of possibilities, right? So let's think about a much simpler situation where there's just 1 red ball and 2 white balls. If they're numbered 1, 2, 3, then having the red ball with 1 and the white ball with 2 would be a different outcome than this, because I can tell when I pick them, I can see this one was numbered 1, and that was, like, the numbers are on the ball, let's say. That one's numbered 1, that one's numbered 2. However, if these have no numbers, I pick this one and this one, it's the same outcome as picking this one and this one, because they're all identical balls. So it changes the number of total outcomes, right? In this one, if I pick 2 balls, I've got these 3 possibilities. However, if they weren't numbered, I would only have this possibility that happens, well, I have this possibility and this possibility, but this one's twice as likely as that one. However,
Basically, you're talking about odds. Like, once you pick a red ball, the odds of getting a white ball is 100% no matter what.
that's true, yeah.
Whereas if you number it,
Yeah, and essentially, here when they're numbered, I've got these 3 possibilities. When they're not numbered, it sort of merges these 2 possibilities into one thing that we, yeah. It's not quite a permutation, no. So here, actually, the order doesn't really matter. So I'm not saying I necessarily get, like I'm not picking the balls out necessarily in order. Like all I care in my outcome is like what balls I have, not which order I got them. Yeah. So if my outcome is just like a bunch of, like a bin full of 5 balls where 3 are red and 2 are white, there's 5 for the 3 numbers that are on those balls, there's 5 choose 3 different outcomes because I'm already assuming they're red. There's 5 reds in total. I'm picking 3 of them. There's 2 possible, or 10 choose 2 outcomes for those. Yep. That might be a better, yeah, if it was a maximum of 3. Well, you could add up 0 red balls plus 1 plus 2 plus 3, or you could say, look at all the possibilities and subtract where you get 4 or 5. That's probably, so it probably is better to subtract in that case. Yeah. Okay. What if I ask for the percentage? Actually, I'll keep that. Of outcomes have exactly 3 red balls. And again, I'm picking 5 total. Yeah. It's gonna involve the total outcomes. I wouldn't subtract though. I would divide, because if you say what's the percentage of people with red hair or something, you count up the red hair people, you then take the total number and you divide, right? So this is the same thing. This is saying how many, so you take the total number that satisfy the criteria that you have 3 red balls, and then you divide by the total number of outcomes. But is it obvious what the total number of outcomes are here? Yep. Right, because, yeah, you've got 15 balls, they're all numbered. You're choosing 5 of them. It's going to be 15 choose 5. Which I didn't actually compute this before class, but this will give you some decimal number, and then multiply it by 100, and you get the percent, right? Yeah. So yeah, if I times that by 100, that'll tell me the percent. But okay, yeah. So it's about 15%. If you had this on a test, we'll try to be careful to like tell you how many decimal places, or whatever, but yeah. Any questions? Okay. This is actually, by the way, a bit of foreshadowing, because I think the next chapter after this is probability, and so we'll be looking at questions kind of like this, because this is kind of telling you, if I picked at random 5 balls, you'd have about a 15% probability of having 3 reds. Right? Okay. So I want to start now the binomial theorem. And then we'll finish this next time. So the binomial theorem is a sort of nice, it kind of gives you a nice connection between something that looks just algebraic, like expanding polynomial polynomial expressions, like expanding x plus y to the n or something. So it gives you this connection between this kind of algebraic thing and counting problems like n choose, these combination problems. So to kind of get warmed up, let's remember how to expand. So this is like FOIL or whatever. Right, x plus y squared, it's x plus y times x plus y. You kind of take this, first times the first, first times the second, second times the first, second times the second. Right, you got to do like this. So x squared plus xy plus yx plus y squared. Actually, just for fun, let's call, instead of writing x squared, I'm going to write xx. I'm going to write yy. But obviously that's the same thing, right? X times x is x squared. So you've got x times x plus 2 times x times y plus y times y. Okay. If we're looking at x plus y cubed, okay, you could, like, what you might be tempted to do is like expand that product and then expand the product of whatever you get here with the last thing. But there's kind of a faster way of doing it. Like, to expand this, what you do is you go through all the different ways to pick one thing from the first parentheses. So I pick the x, pick one thing from here and pick one thing from here, and go through all the possibilities. So x, 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 y, x, y, x, x, y, y, and so on and so forth. So that's kind of a faster way of expanding these kinds of things. If I do x, 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 so, well, that's x cubed, but I'll write it x, 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 y, x, y, x, x, y, 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 x, x, y, x, y. There's no right and wrong way to do this, but you just have to get every possibility exactly once. Y, y, y. Okay. If you collect up the terms, you'll see that your coefficients are 1, 3, 3, 1, right? Okay. Something I want to kind of to tell you about is, well, I mean, when I'm doing this, like it just sort of seems like these numbers 2 and 3, they kind of come out of nowhere. But they don't actually come out of nowhere. There's a good reason for those numbers. Actually, before I tell you the general principle, let me just show you. So I'll just write it down, but you can check it yourself, that if I do to the power 4, I have xxxx plus 4, xx, xy plus 6, x, x, y, y, plus 4, x, y, 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 plus y, 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 y. Or sorry, x, y, yeah. Okay. So yeah, what I'm trying to say is these numbers don't just come from nowhere. There's something special about, why does the numbers 4, 6, and 4 show up there? And that's because of the binomial theorem. So you can, if you think about it, so if you compute 4 choose 0, it's equal to 1. 4 choose 1 is equal to 4. 4 choose 2 is 6. 4 choose 3 is 1. Or sorry, 4, I mean. 4 choose 4 is 1. So that's where these coefficients come from. So generally speaking, if I want to expand x plus y to the n for some integer n, positive integer n, that's always equal to n choose 0, x to the n, plus n choose 1, x to the n minus 1 times y, plus n choose 2, x to the n minus 2, y squared, plus dot, dot, dot. Yeah, here maybe I should put y to the 0. Okay. So this is what the binomial theorem. Is it clear what I'm trying to write here? That the coefficient of x to the n is n choose 0, which is 1. Coefficient of x to the n minus 1 times y is n choose 1, and so on. Okay. And there is a reason for this. So the reason kind of comes from, if you think about what I've written here. So if I say, suppose I'm going to pick one x or y from each of these factors, I could say, how many ways can I choose x or y, and then x or y, so that there's exactly one x? Well, that's 3 choose 1, right? I'm making 3 choices. One of them has to be an x, so it should be 3 choose 1, which is 3. Okay, so we'll continue this. We'll review this next time and work on some problems involving it.